Hello everybody, here we are, and this is the time to just simply talk about some of the things. Mainly we will be talking about this thing, web dev project ultimately, and WebRTC theory. WebRTC has been a pending topic for a long time, so first of all we will be getting started with that only, and then we'll be switching to the remaining things. Even I learned about just a little bit ultimately how unit testing works and all. So we will be going through all those things. Having said that, the primary focus is gonna be on the WebRTC theory. We will not be doing these things practically because of course practical things take time, and we have already built such a clone of Google Meet and all. So ultimately we have already built video callings application, so we do not need to know about the practical stuff. We do not need to worry about that. Okay. And as for right now, I hope I'm audible. The fan is running in the background, so there's gonna be some noise as well. Going ahead, we have to talk about WebRTC theory. So let's simply get started. I'd better open up what? Xcalidro, spin up Xcalidro here. Xcalidro. Just gonna be going on this website, and I'm gonna be drawing the stuff if needed. And apart from this particular thing, let me spin a barrier too. What's the IP? So that is, just a minute, let me enter the right IP here, and then the job will be done. 7 point this point 19. Let me start this. Started. Let me start this as well. And alrighty, the job is done. Alrighty, so first of all we are gonna be talking about WebRTC here, and whatever I have in my notes, I'm just simply gonna be, it is actually gonna be a recap. A long time ago I went through this thing, so this is gonna be WebRTC theory recap, exactly theory recap, how the things work in action, like in theory. And as for doing it practical, we have already done that, so it should not be problematic. Wow, this is amazing actually. So we are mainly gonna be talking about this theory part here, and let's see how many things we can cover. Just a minute, let me open my notes as well, and then we'll get going. And notes. Okay, just a sec. Okay, software and Udemy and WebRTC, that is this one. Alrighty, talking about the WebRTC, first of all, the thing that I actually learned in this particular section, that was IIFE, that simply means immediately invoked function. So there are functions like this. So these are the immediately invoked function. So it is, the expression actually sort of looks like this. Inside the first one you can write whatever you need to just simply run, and inside this is just simply calling that particular function. So this is the expression of immediately invoked function. So having said that, just inside this I can have a function, and that will be running suppose console.log. Hi there, this function is gonna be running, so whenever the program any file runs, this will automatically run directly. So these are called immediately invoked functions. So we just talked about all these things verbally, and we will be doing the same thing only. Then window.location origin, that's interesting. Let me even go through it well. There are few things that first of all, there is this window object dot location we have what is the type of the window here anyway? Type of window, this is an object. Okay, so we have window dot location gives me what? It just simply gives me a lot of things in the sense it gives me the port number, there's no port as such, path name slash, let me make it like this, localhost 3000, even if I'm not gonna get anything. But if I write a window dot location right now, it's gonna give me some result. So doesn't it have any result right now? Port number doesn't, it's not there. It turns out that there should be proper website for that. Okay, never mind. So we get port number, path name, origin, href, and host name, host, and ultimately things do not have proper values because no application is running as such. Not a problem, but okay, these are the things that we get here. So especially when it comes to origin, so we get the whole URL. When it comes to the host, so we get uh, sort of the host plus the origin. I mean, when it comes to the origin, so window.location.origin, that gives me the whole URL, so whole origin ultimately, and then location.host gives me the host plus the port number, host name gives me just the host name, hrefs gives me the whole href, ultimately whole URL, and path name gives me the subdomain ultimately, then window.location port gives me the port number, protocol gives me the protocol, search gives me the extra searching stuff that is there. So okay, let's not worry about them. These are the just the extra stuff, the thing that we actually have to focus on. That is the WebRTC theory, right? So let's go through the introduction. Again, in the introduction what I have here, I can just show you directly from here, that would be better. So first of all, we talked about this thing, that's actually a better thing. I thought of not keeping this thing on my main screen, but it's better to actually have it. So we talked about immediately invoke the function. This is how it just simply goes on. We have some of the extra things like window.location.origin, of course, gives you the origin. That is not the whole URL, but ultimately the main origin you get over here. And then host gives you the host name plus the port number. Host name gives you just the host name. href gives you the whole URL. Path name just gives you the path that is there at the end, sort of you can call it extra routes that you have. And then port gives you the port number. Video.protocol gives you the protocol, which protocol is actually being used. Search gives you the extra searching things. They can actually be the parameters, query parameters and all. Okay, so we have talked about this. Let's simply get going, and we are going to be talking about the introduction. Over here I have just simply normal HTML file. The good thing that need to be noticed, that is this video tag. So we have this video tag, and the thing is that from your device you can easily get the video source ultimately. So what am I doing over here? My video container. So whenever I'm clicking on that particular video, so navigator media devices get user media, so you can get the user media if that's available, of course. And here you can just simply say video true, so video is gonna be available. Audio true, audio will be available. And you can even specify the ID of the video. So here I'm just simply specifying the device ID, and that if the device ID matches this particular ID, then that particular device simply said, if you have two cameras, those on your device, that could be any device, be it the laptop or the computer. So if you have any device, if you have two cameras, that simply means more than one camera. If there's only one, it will select that directly. If there are more than one, then of course you will have to make sure that the right ID is specified over here, so that on the basis of that particular ID, it is actually able to select the right device. And then once you got the user media, then user media will be giving you the streams. Again, once you got the stream, you can just simply add the stream. Pretty simple, makes sense, and this is how it just simply goes on. And apart from this particular thing, ultimately once you got the user media will automatically give you the stream, and that is it. This is how it goes. And video navigator media devices, enumerate devices. This is just a method that just simply gives you the information of all the devices. So it will give you the list of all the devices. You can just simply loop you can just simply run a for each loop on them, and then you are gonna be getting the device info. A device info will actually contain the ID that you actually need. So first of all, if you have more than one devices, that simply means you need the ID to make one camera, to enable one camera or the other. So for that thing, you need to have the ID, and you can actually get the ID from here. So whenever you want to get the ID, you have to just use this particular method. The job will be done. Okay, so these are the things that we are just simply gonna be talking about them verbally. It is just the recap part, so that I don't forget the theory stuff. It's been quite long time, so that is why I'm just simply going through it. Then we have these other things. These are actually the special ones that we have to talk about. We have net ICE framework, the role of ICE frameworks, ICE candidates, and all. We have tons of things, and especially I have written a lot of them here. So let's simply go through them one by one. So first of all, we have net. Again, if you want to get the IP address, so you have to just simply run this command, and netstat will give me what? Not sure about this particular thing. IPA gives me the IP address related info, and then there's another one, netstat. It just simply gives me the information, the network status. Yeah, I think so. It just simply let me know about the processes that are running, if I'm not wrong. netstat command use for. So what is the use of this command? So netstat network statistics command is versatile command tool used for monitoring network activity, diagnosis, connectivity issues. Okay, it is mainly used for networking activities, and we just got the right result anyway. Going for further from here, every device on the web has to have an identity IP address. That is right. NAT allows IP address sharing. Many devices on the LAN local area network can share one WAN wide area network globally. Many devices on LAN local area network can share one WAN. So ultimately there's gonna be one wide area network that will have its own IP address, and that WAN will be connected to LAN. That simply means local area network, and there can be many devices connected to that local area network. So WAN will have its own IP address. The main thing is that WAN over LAN over here. So ultimately local area network will have its own public IP address, and there are gonna be sort of router, call it router of course. So the router will have its own public address, and then many devices are going to be connected to this. So those devices, they will have their own private IP addresses, and router primarily implement NAT. So yeah, router has been even mentioned over here. So it's sort of going to be like this. You have a router, that many devices are connected to that particular router, and the router is sort of LAN, local area network of course, and then many devices are connected to that. Hence those devices get the private IP addresses. Yeah, sort of that, and that is it. This is how it just simply goes on. And when it comes to NAT, so NAT is just simply used for mapping. So it maps the public IP address and the private IP address of the devices, and this is how it just simply goes on. Your router will create a table that maps, yeah, that's it, this is it. Your router will create a table that maps all active connections between internal private IP addresses and their corresponding external IP addresses. This is how it just simply goes on. So there is something called NAT. Okay, this is mainly used for mapping, and your router does this job. So suppose there is a router and many devices are connected to that router. So whenever a request goes, so the request go via the router. So when the request goes, whenever the connection gets established, so at that time NAT mapping will be done. So a mapping, what is the full form of NAT? I've forgotten. But ultimately sort of a mapping will be done. In that mapping there's going to be private IP address and there's going to be public IP address, and that is it. So the request will go, you will send the request using private IP address to the router will forward the request using public IP address, and then it will go to the internet. Then you will get the response back of course, and our router will receive the response, and then router will forward the, because router has the mapping, router will know which IP address, private IP address sent the request back then, so it will just simply forward the request there. So this is how just simply gonna be going on. Talking about type of NAT, first of all, what is the full network address translation? Okay, this is the full form of NAT. So NAT has this particular short form, that's get a full form. Then there are different types. We have static NAT, we have dynamic NAT, we have PAT, port address translation. That's interesting. Static NAT and we have dynamic NAT. So ultimately two types of NATs we have, and there is something called PAT, port address translation. We have network address translation, we have port address translation. Okay, never mind. Let's go ahead. Problem and solution. What is the problem? Individual computers may not have a unique IP address. Device IP address can change when moving between networks or due to NAT changes. TCP, transmission control protocol, UDP, user diagram protocol. We know about these things. We talked about these are the protocols that are used on transport layer. So there are different layers, right? So if you learnt about OSI model, so in the OSI model we have application layer, then we have presentation layer, then we have session layer, then we have transport layer, then we have data link layer, then we have network layer, then data link layer, and then you have your physical layer. So when it comes to physical layer, this is application layer mainly used for showing you the things like the way I'm getting application layer is mainly responsible for showing you the application, as simple as that, keep it like that. Then we have after application layer we have presentation layer. Presentation layer is mainly used for formatting the data. So application layer collects the data, sends the data to the presentation layer, that is mainly responsible for formatting the data in the right format. And once this is done, so after presentation layer we have session layer that makes sure that if there is a connection between two clients, that sort of handles the session related stuff. So if there is a session between the clients, that's gonna be established, and that's gonna be, I mean, if there's active session, so that's gonna be maintained by session layer. So we talked about this as well. Again, this is the most basic thing we are talking about. There's, if you actually want to dive deeper into them, there's a lot to just know about. But okay, let's forget about them. So session layer is done. After session layer, we have transport layer that is mainly responsible for transporting the data. So we have TCP and UDP protocols being used over there, and TCP is transmission control protocol, UDP user datagram protocol. Again, they are used for different purposes. We are not going to be talking about them. After transmission layer, we have network layer. So what happens that in the transport layer, not in transmission layer, in the transport layer, data is actually converted into segments, and once the data is actually converted into segments, then that data is actually sent to the network layer, and in the network layer, the data is converted into packets. So many segments get combined and they are converted into packets, and some more headers are added there. Again, I'm not gonna be talking about that, but overall this is what happens. And so in the network layer, some more packets are added with the extra headers. Of course, it contains the IP addresses and all, and then it goes to the data link layer. In the data link layer, those packets get converted into frames. So ultimately packets are framed into frames, and then again extra headers are added there, and then they are forwarded to the physical layer, and physical layer is responsible for sending them to the other client. So this is how the overall flow looks like. Again, I'm gonna be talking about everything verbally over here. Do not expect me to just simply do anything, because we have a lot to discuss, especially talking them verbally. If I keep talking about them verbally, then only it is possible to get them done. By the way, this is I got these images especially from one of the courses. Gonna be using them to just simply revise. Okay, every unique network or connection which includes WebRTC is identified by a 5 tuple which consists of five specific parameters that collectively provide a distinct identifier for that connection. The components are this. Ultimately, if you want to make a WebRTC connection between two clients, so these are the things that you have to keep in mind. So source IP address, destination IP address, source port number, destination port number, transport protocol. Pretty simple. If there are two clients, they want to talk to each other, so there should be source IP address and there should be destination IP address. There should be source port number, there should be destination port number, and there should be protocol, like which protocol is going to be actually used, TCP or UDP. By the way, source IP address, this is the IP address of your device, the device initiating the WebRTC connection. For example, this info may contain both your public IP address and private IP address. You must be knowing that your device is ultimately connected to a router. So that router will give you the private IP address to your device. So ultimately, this is going to be the combination of both private and public. This is how it's going to be going on. And destination IP address, this is the IP address of the WebRTC device you intend to connect. This may contain both their public IP address and their private IP address. We have source port number, this is the port number that your browser has allocated to your PC. As simple as that, your browser allocates. So it could be 3000, it could be 4000, or any port for that sake. For the WebRTC connection, which is typically dynamically assigned internally for WebRTC, I was talking about 4000, 3000. For the WebRTC connection, which is typically a dynamically assigned ephemeral port, that is around this much. So ultimately, port number is going to be dynamically assigned. When making a WebRTC connection, you do not really worry about the port, right? You can run your application on port 3000 or 4000, but when the WebRTC connection establishes, at that time it's going to be using its own port number, and that makes sense. Alright, destination port number, this is the port number on the destination device that you are wanting to establish a connection with. For HTTP, this will be port 80 or port 443 ultimately. But for WebRTC, this will be the other user's private port number. Okay, so just like that, when you are running something on your local device, suppose an application, so that may be running on port 3000 or port 4000. Alrighty, if there's any service, suppose Nginx and all, that may be running on port 80, of course. So if there's any application that you are running, that will be running on the specified port that you have specified. Once you build the WebRTC connection, those WebRTC will automatically select the right port, within this range 49152 to 65535. Similarly, it's the same thing is going to happen on the other side as well. And as for the HTTP, they use 80 or 443, everyone knows. And for the WebRTC, that's going to be the private port, and private port will be selected by the what? By the WebRTC only. So WebRTC will select its port from within this range. Okay, let's continue. And the transport protocol, this indicates the protocol used for communication. WebRTC uses either TCP, transmission control protocol, or UDP, user datagram protocol. So this particular thing is done. And continuing from here, each ICE candidate is assigned a priority value, which is a number ranging from 0 to this particular one. A higher value indicates more desirable candidate for establishing a connection. The browser's ICE agent is responsible for setting those browser's ICE agent is responsible for setting those priority values according to the ICE specification outlined by the IETF. This is just a protocol. Keeping in mind, if you want to make a connection between two clients, there are gonna be ICE candidates. So first of all, there is something called ICE I forgotten ICE agents. They are mainly responsible for, even before that you have to know that there are ICE agents. They are responsible for generating the clients, and they rank not clients actually, they are responsible for generating the candidates, ICE candidates, and they just simply give the priority values to those ICE candidates. The higher the values, the higher the priorities. This is how it's gonna be going on. So ultimately this is how it's gonna be going. Overall things are gonna be like, so you have a laptop, and there's gonna be another client on the other side. So there can be many candidates on your side. So candidate 1, candidate 2, candidate 3, then can be many of them, and they may be using TCP protocol, they may be using UDP protocol. You will have your private port number, you will have your private IP. Similarly over here you will have the same thing, and over here you have the same thing. So the IP address, of course, it may change. Over here you have the same IP address, on the other device you will have the different one, depends on your router. And then that's gonna be net mapping. Ultimately router will maintain a kind of a map of your private IP and public IP, and then the request will be forwarded to the other device. So this is how it's gonna be going on. The important thing is that it could be that you are sending a request to the another device on the internet, and at that time router will be forwarding the request to that particular device. It could also be that you are just simply sending the request to the other device in the same network. So when the request goes to the router will check whether this is for the device on the internet, other device on the internet, or this the another device actually is in the same network only. So if the device is in the same network, then it will just simply directly forward the request there. So this is how it's gonna be going on. Having said that, what I mean that it may be using your host network, it may be using the device may be in your host network, ultimately your own network. In that case the request will directly reach to that particular device. If that is somewhere on the internet, in that case Eastern servers are gonna be used. What are the Eastern servers? Eastern servers, to those you just simply send your request. They just simply give you tell you about your public IP and public IP address and port number and all, and then you just simply send the request to the other client. So again we are going to be discussing about them as the time comes. Just a sec, give me a moment. Alrighty, I hope I haven't cancelled anything. Okay, moving further. So okay, we have talked about this. This is sort of the ICE framework. Okay, and now how much we are going to be discussing about the theory. Overall things are simple, right? Set up RTC peer connection, let a PC, this is how it's going to be set up. Add information about the data you wish to send or receive to your peer object. That's simple. Once the peer connection is ready, you can just simply add your streams and all over there. Then after that you have to create the offer. Once the offer is created, don't forget about the connection. You need to gather information about the others can find you. So you will get your ICE candidates, you will send the ICE candidates. Ultimately this is how it's going to be going on. So what is going to be happening, the overall flow, how it's going to be going on? It's pretty simple. On your side you will generate the peer connection. Once the peer connection is created, you will add some streams to that. Once the streams are added, then candidates are going to be created. Once the candidates are created, candidates will contain what? Candidates will contain your information. They will be about you, who are you exactly, and then those candidates are going to be sent to the other peer. then they will know about you. Similarly, those other peer will send the candidates to you, so you will know about that particular candidate. So both of you know about each other, then you guys can simply connect. Let's talk about ICE framework. The process to find the device on the internet. ICE frameworks. Okay, so when you create a RTC peer connection object and set up your WebRTC application, your browser will automatically gather information about your PC's identity, so that another peer can find you. As simple as that. It may contain public IP, private IP, public port, private port. So public IP from outsiders view. So ultimately, your public IP is public IP from the other outsiders. Other peers view, and then you have your own private IP in under your LAN. Of course, so there is your LAN connection. Then there is the router. Router just simply gives you the private IP and the port, transport protocol, and all these things are gonna be there. So in reality, most devices live behind the net. That is right. WebRTC applications use ICE framework to overcome the complexities of real-world networking. ICE tries to find the best path. ICE framework ICE candidates ultimately tries to find the best path or the candidate to connect peers. Every browser has an ICE agent that allows to try and find the best possible routes ICE candidates to, of course, to your PC. The ICE agent operates within the browser's WebRTC implementation. That is right. It is integrated into RTCP peer connection object. So ultimately, this is how it simply goes. Once you create your RTCP peer connection, so there is something called ICE agent that is again in your browser itself. So like RTCP peer connection, this whole class is in your browser. Similarly, ICE agents are in your browser. So as soon as that particular class is instantiated, and ultimately you get the object, then ICE candidates are gonna be created, and ICE agent will be responsible for giving the priority to those candidates, because many candidates are gonna be created. Many candidates in the sense, some maybe use from your host device, and host local network, ultimately host network, and they are gonna be making the request to the local device only. So ultimately, there can be some candidates, they may use your local network and ultimately host network, and there are gonna be some that are gonna be using Eastern server, and some may be using TCP connection, some may be using TCP protocol, some may be using UDP protocol. So ultimately, this way you will have many candidates, and those candidates will have the priority, and on the basis of the priority, they are gonna be selected exactly which one is gonna be the best one for making a connection. Again, all these things you do not need to worry about it. You just simply send the ICE candidates, all the ICE candidates to the other peer. Other peer simply sends all the ICE candidates to you. ICE agent automatically selects the best one, and it just simply gets the peer connection established. So you do not need to worry about choosing the best one manually. Alrighty, the process to find a device on the internet. Collection of ICE candidates is referred to as gathering phase. So collection of ICE candidates, okay, is referred to as gathering phase. This is triggered by the addition of a new media section to your local session description. I mean, it's pretty simple. Whenever you add something to your local description, at the time your ICE candidates gathering process will actually start. When a new gathering phase starts, ICE agent will notify RTCP peer connection object of that gathering is occurring through a state change event. That's right. When a new ICE candidate becomes available, the ICE agent will supply it to the RTCP peer connection object via an on ICE candidate event. Ultimately, what is happening that as soon as you added something, ultimately you added your local description. First of all, what will happen? Let's keep it like this: that you have your peer connection established. Once the peer connection is established, then you are gonna be create the offer. But even before creating the offer, you will add some streams and all to your peer connection. Once the streams are added, then something will change in the peer connection, of course. So whenever some kind of media changes, at that time you are gonna be adding. You will create the offer, and you will add the offer to the peer connection, and as soon as the offer is added to the peer connection, ultimately offers are there added to the local description. So as soon as local description is set, your ICE candidate gathering process will start. I mean, again, if you know about it, that would be great. If you don't know, it's gonna go over your head. So when a new ICE candidate becomes available, the ICE agent will supply it to the RTCP peer connection object via an on ICE candidate event. So ultimately, using this particular event, you are going to be getting the list of all the ICE candidates that have been created. These candidates will automatically be added to the local session description by the ICE agents. So the candidates that you get, so ICE agent will be responsible for directly adding them to the local session description. That's interesting. The thing is that when it comes to the local description contains many things. Local description has the information about your offer. It also has the information about all the candidates. When all candidates have been gathered, a final on candidate event will be emitted with the value of null, that's right, to signal that gathering process is complete. So ultimately you will keep getting the candidates, and once everything is done, then you will get the last candidate that will have null value. That simply means ICE gathering process is it's done. By the way, when it comes to ICE gathering state, that can be new, that can be gathering, and that can be complete. So new in the sense that hasn't even started. That's just the new correction. Gathering means okay, the local description got set, hence gathering process started, and then it can just simply complete it. It can get completed. Okay, event listen. ICE gathering state change. ICE gathering state can be new, connected, and completed. It just simply tells you about the state of the ICE connection. Pretty simple. A connected state indicates, it's gonna be too much here. I thought it would not take a lot of time, but it will take time. We have to talk about many things. Never mind, I'm gonna go through them really quick. So it can be this. A connected state indicates that usable connection has been established, but ICE agent may still be checking for the better candidate. So whenever, as soon as it is connected, so this state can actually be connected, and then it can be completed, I think. So connected means it may still be looking for a better connection, and then there is something called completed state. Goes one step further by signifying that all candidates pairs have been checked and connection is confirmed for all components. Again, we could have done all these things practically as well, but it takes a lot of time, and hence it is not really possible to get everything done in one video. Links for WebRTC internals. So by the way, these are the links for just simply checking the status of your WebRTC connection that has been established. This is merely for the Chrome or any browser that uses V8 engine, and then this is for the Firefox about WebRTC. Ultimately, this is nothing but the URL. So if you have your WebRTC connection established, just paste it there and you will know about that. Alrighty, so we have few things over here. We have RID, LID, PID of course process ID, and there are some more. So there is some, first of all, RID. Again, the render ID helps to track which browser tab is associated with the peer connection, because there can be multiple browser tabs, that is right. So render ID is responsible for tracking the tab. Ultimately, it is gonna be checking as if which browser tab is associated with that particular peer connection. So there can be multiple peer connections in multiple browsers tabs. Hence, RID is responsible for associating the right tab to the right connection. Okay, LID, then we have local ID, is assigned to the peer connection instance and helps uniquely identify it within the rendering process. So LID is responsible for local ID is responsible for identifying the peer connection in the within the rendering process. Okay, and then we have PID. Each tab in the browser runs in a separate process, and knowing the PID allows for efficiently handling this process. Okay, that's pretty simple. So we have few IDs. Again, when you get it, whenever your peer connection is ready, you will get it. You will get your URL. On this particular URL, your application is running, and as the peer WebRTC connection, of course, you will get the RID, render ID, local ID, PID, process ID. You are going to be getting all these things. So it is sort of done. This is how it's going to be going on. We have session description anyway. Session description. There can be two types of session descriptions: local description, remote description. Local description is for the local user, remote description is for the remote user, of course. So you will have the remote information over there. Let's simply go through it well. First of all, just a minute, give a sec. Alrighty, sorry for the delay, let's simply continue. So we were talking about this info about the WebRTC connection. So ultimately, session description stores just information either about you or about the remote user. So you need to create a set of instruction session description that tells two devices like computers or smartphones how to communicate with each other. So you need to have session description that will mainly contain the information, and that information can be local. It can either be local description or the remote description. Set local description after you create offer and answer. That's right. And remote description. That's simply okay. That's bad. Never mind. It just simply contains the remote users. So if you get an offer from the remote user, so that offer will be set over here. And similarly, once you send the answer from your side to the other user, that answer will be set over here. So remote description can actually contain remote offer and answer. Local description can contain local and local offer and answer. It's just like that. And then apart from this particular thing, this is what you get in the description. So there's the version, there's output, there's origin actually, there's session time, there are attributes. So version just simply tells you about the version, and then you have this origin that simply tells you about your IP address over here. It just simply tells you that this is gonna be using IPv4 using internet. If I'm not wrong, that's what it is, a spice, and there are some other numbers, you can know more about them. And then we have the session name. It just simply tells you about the session, it tells you the time, and then there are some other attributes that it has. Okay, how can you know about it? So once you create the offer, then when you set the offer, once the offer is set to the local description, then you can log the value of the local description. And the question is, how will you be logging the value of the local description? So once you create the peer connection, you automatically get that value. Ultimately what I mean, not this actually, const pc, that's gonna be new rtc peer connection. Once the peer connection is created, if you just run pc over here, so you have these things, pc dot local description. It is null right now, but once it is added, you are gonna be, no, this is just a value. So once that is added, so instead of getting null over here, you will get the exact value. So this is how you can just simply go ahead. Again, doing the things practically is not really the goal. Talking about the things just theoretically is the goal right here. And once we've gone through this, every WebRTC connection is managed by session description. So that's right. Each peer will have their own local description, a PC local description, and the other peer session description, remote PC description. That's right. The information contained inside of this description object is governed by the rules set by JSF. This is again a protocol. Do not be, of course, we have to worry about it. Let's read more about it. So JSF is like a traffic controller. So SDP is the language that JSF uses to describe the WebRTC session. That's right. Ultimately, SDP stands for Session Description Protocol. I hope so. I'm not sure about the full form of it, but ultimately, what happens that SDP, whenever you create the offer, your offer contains SDP. Your offer contains two things. Your offer or the answer contains either the type can be either offer or answer, and then it contains the SDP information. Session description. I hope the full form is protocol. Okay, so JSF's session description use session description protocol, SDP session description protocol. Yeah, that's right. Syntax for their internal representation. This is a format to just simply contain the information. So it will sort of have the key value pairs, not exactly key value pairs, but it looks like that anyway. While this format is not optimal for manipulation from JavaScript, it is widely accepted and is frequently updated with the new features. Any alternate encoding session descriptions would have to keep pace with the changes to SDP, at least until the time that this encoding eclipse the SDP in popularity. Okay, forget about this. Ultimately, SDP is used for sending the information. So even if you are creating your offer, SDP is gonna be there. JSF does not force us to use any particular signaling model or state machine, but it does force us to record and exchange the session description in the fashion described by this particular whatever this is. Let's not worry about that, but ultimately you have to keep two things in mind: offer and answer. So as per this overall protocol, as per this JSF, you have to keep two type can be offer and answer, and then you will have your SDP over there. JSIP also manages the format of ICE candidates and adds them to the local description accordingly. JSIP also manages the format of ICE candidates and adds them to the local description accordingly. Ultimately, description contains both the things. It contains your candidate's information, it contains your offer or answer information, as simple as that. So whenever new candidates are created, it just simply adds the information over there, and JSIP is responsible for that. That's great. And ICE gathering process, this is how the overall things look like. So ultimately, whenever your WebRTC connection establishes, at the time offer is gonna be created, then negotiation needed will happen, then create offer on success. Ultimately, these are the events that get triggered, and the on negotiation needed event is fired before calling a pc.create offer. The on negotiation event is fired before calling this. So why is it pc.create offer? Whenever something changes in the peer connection, so at that time on negotiation needed method will be event will be triggered. For over here it just simply shows after that, but in reality it is triggered before that. So that's what is mentioned over here. So the on negotiation event is fired before calling pc.create offer. That's right. So why is it showing after create offer here? Well, events like on negotiation needed are processed asynchronously and may appear in logs after certain operations complete. Even they were triggered beforehand. That's right. This can create the illusion that calling create offer directly caused the event when it fact indeed done. Yeah, that's right. So ultimately, on negotiation needed, this was actually triggered before create offer, and after that create offer we actually created the offer. But here it doesn't seem to be like that. It is saying that first of all create offer and then on negotiation needed. This is mainly because that is asynchronous, and that just simply takes some time to just simply get done. Okay. Anyway, user fragment. There are gonna be user fragment information anyway. So ICE adds ICE gathering process to the WebRTC connection. There are these user fragments, and they are the part of the ICE candidates, and these are the user fragments here. It adds ICE gathering process to this WebRTC connection. ICE gathering process to this WebRTC connection. What does it mean? Adds ICE gathering process to this WebRTC connection. That simply means as soon as you have user fragments over here, they are mainly responsible for adding the ICE gathering process. Let me see. User, what is the name, bro? Just a sec. Username fragment, huge. Oh, am I facing the network issue? I am, or ain't I? Forget about this, let's continue. We have to talk a lot of things. Username fragment user in WebRTC. Here we are. So the username fragment, often called a DU frag, okay, that's our ICE frag in WebRTC, is crucial component of ICE interactive connectivity establishment protocol used to establish peer-to-peer connections. It is randomly generated. That's right. What is the use of it? Okay, uniquely identifies a single. Okay, that uniquely identifies a single ongoing ICE interaction session between two peers. So it is merely for responsible for session. Okay, let's not worry about that. Ultimately, if you understood something, that's great. If you don't, forget about that. Overall, we don't even need to worry about all these things when a real WebRTC connection gets established. Okay, so add ICE gathering process to this WebRTC connection. So ultimately, ICE gathering process gets added to the WebRTC. That simply means it is responsible for creating the connection between two peers. Okay. So this particular thing is done as well. So session is done. The role of ICE servers. So let's talk. There are three servers actually. Stun and turn. Let's see. Role of the ICE servers. While tools like ipconfig and netstat offer valuable insights into network configurations, they are just the starting point and often insufficient for WebRTC applications. Each WebRTC connection also requires a unique port, and while it's theoretically possible to manage this manually, this approach is impractical. This is where interactive connectivity establishment (ICE) servers become essential. ICE servers facilitate net traversal. So there is something called net traversal. That's right. The ICE protocol addresses the challenges posed by nets and firewalls through a process known as ICE gathering, where devices exchange network addresses called ICE candidates. So ultimately there are ICE servers and ICE agents. ICE agents uses ICE servers, and ultimately they create ICE candidates. So it is just simply saying that you can actually get the IP address and IP address of your device and port number and then send it to the other client, but it is not feasible, and there are tons of things that you have to take care of. Hence there are something called ICE servers. They just simply generate, they are responsible for generating the ICE candidates. Again, ICE agents work behind the scene, so ICE agents are responsible for managing everything. ICE agents use ICE servers and all, if I'm not wrong, and then ICE server ultimately generate the ICE candidates, and that's the simple thing. Let's talk about ICE candidates over here. So the ICE agent is responsible for creating ICE candidates and adding them to your local session description. Candidates are automatically added, especially if they are the local candidates. That's right. However, you really wanted to, if you really wanted to, you could create your own ICE candidates and add them to your local description manually. Well, we do not, at least I'm not gonna be doing that, but yeah, this is also possible to do. So new RTC ICE candidate name, exactly, candidate, and it will have some more information over there. SDP mid, SDPM line index. This is just the example, you can know more about it, and ultimately this is how it simply works. So you can create your own ICE candidate. By the way, ICE candidates are by default created by ICE agents, and ICE servers are responsible for ICE servers are the ones that actually create it. And the value of a mid can be any what is this now? We are talking about a mid 0. This represents the media, if I'm not wrong. Let me see. The value of a mid can be any string bit that uniquely identifies the media stream. In our case here, we are seeing a mid 0, indicating that this is the first media stream in the SDP description. The numbering 0, etc. It can be anything, often used to represent the order of media streams. So ultimately, there can be many media streams, and the number over here that simply represents the number of the media streams that you actually have in your device. Okay, then SDPM line index provides ICE agents a simple way to reference the position of media stream without needing to parse the SDP string. That went over my head. Okay, so the SDPM line, it was me who just simply took the screenshot, saved it, but it was 3 months back or something. Now here we are going through it again. So the SDPM line index provides the ICE agent a simple way to reference the position of media stream without needing to pass the SDP string. Again, do you really need to worry about all these things when you are actually creating a video calling application? The answer is no. We don't go through these many things. We just simply create the peer connection, add the streams, and create the offer, send the offer to the other clients, and just get it done. And it's good to, that is why I'm just simply going through it, because it's good to just simply know about the things in depth too, right? So SDPM line just simply make sure that you are able to find the right media, and so that you do not need to parse it. It makes sense, because if there is SDP, what happens here, that you have your SDP, it is sort of the configuration, right? So if you want to know something from the SDP, then you will have to parse that, and this SDPM line index will just simply tell you the line, this is the line, over there you will find the media stream, and that is the job will be done. So yeah, that is what it just simply does. Consider an SDP with two media lines. Okay, 2 media lines. Let's see. This is the version. This is the origin, session, time, media, media audio, media audio. This is the port number. This is something. And then we have video. So ultimately there are 2 medias right now. There is this audio media, there is this video media. So there can be 2 medias, of course, media I'm talking about, and hence that's where this SDP line index is gonna be used for. Okay, in this context, the first media line M audio has AM audio, an index of M line index 0. So index is 0 over here, not this. Come on, index is 0 over here, index is 31 over here. So the index may keep changing. M ultimately audio has index 0, video has index 31. So M line index is 0, 31 or 1. It seems to be 1, but okay, it is actually 1, but it's mentioned as 31. Never mind. Okay, let's talk about this. JSEP requires that every ICE candidate is placed in an ICE candidate object. Every ICE candidate is placed in an ICE candidate object. That's right. I mean, when it comes to ICE candidates, so they are nothing but the objects, right? So you have the whole information over there. And when it comes to the information, got that. Candidates are gonna be inside ICE candidates object. So there is gonna be RTC ICE candidate object, and inside that you will have your candidate, and this is the candidate that I'm talking about. So not only that candidate, you will have more things. And when it comes to that particular candidate, so it has the name, it has the protocol, it even has the IP over here. It will have the private IP, public IP, and it will have ultimately many more things. It will even have the host information. Okay, going ahead, each ICE candidate is typically represented as a string in a specified format defined by RFC 5245. This is nothing but a protocol. Okay, the thing that you need to this is the ICE candidates that you generate. So sorry, not ICE candidates, the SDP. So candidate information gets saved in the local description like this. So ultimately, whenever your ICE candidates are created, they get saved in the session description automatically. And you can first of all get your local description. Once you get your local description, then there's gonna be type and there's gonna be SDP. So as I said, the type can be offer or answer. SDP actually contains the value, and inside that you have these many things. So you have origin, you have session, you have time, you have extra things. Ultimately, there can be actually many more things. So let's not worry about them much. But I do have the information about them. So let's read through them. Okay. So first of all, the thing that we get over here, we have the name, then we have this. So that is called candidate ID. So the just after that we get, that is the candidate ID, a unique identifier for this particular candidate. This is nothing but the candidate overall, and candidate contains more information, and we are just simply going through them one by one. And then we have component ID. So indicates that this is the main way to carry the actual data as opposed to stats and quality control. So this is the component ID anyway. Then we have transport protocol, that's UDP in this particular case. It specifies that this candidate uses UDP. Then we have the priority number. This priority number is given by ICE agents, and that's it. On the basis of the priority number, a candidate is selected. The priority value used by ICE candidate to select the best candidate, higher the number, the more priority. IP address, we have the IP address, the local IP address. Port number, we have the port number. Again, the local port on which a user is listening for incoming WebRTC connections. We have type, that is the host. So the type can be string, or type can actually be the host over here. In this particular case, that is the host, and indicates that this is the host candidate, meaning it is generated from local IP address. So ICE candidates can be generated from local host, host machine as well, and they can be generated using Eastern server as well. So generated generation 0. So this 0 that I'm talking about over here, what does it mean? The generation number of this candidate. Okay, user fragments, we have a unique identifier for the WebRTC session. Okay, number, network ID or cost, additional metrics about the network path. Well, we will have what have I done? Okay, done. So in some networks environments, so for example, corporate firewalls, UDP traffic may be blocked entirely. TCP provides a fallback mechanism where connections can be established over TCP instead. So the thing is that by default, whenever you are making WebRTC connection, UDP is going to be used. But if that fails to just simply connect, then TCP is going to be used over there. Hence, TCP protocol is being used here. Protocol 9. This one, so not protocol, actually port 9. 9 is commonly associated with the discard protocol. Actual data sent over this connection is discarded. Okay, that's fine. The browser is signaling support for TCP candidates but has not allowed a valid listening available for port available for establishing a connection. We had 58781, that was the protocol using that was the port when we used the UDP protocol, and over here 9 is the one because TCP UDP ultimately failed to just simply create a connection. It serves serves it serves as a placeholder to indicate the potential for TCP communication. So ultimately, the 9 we have the 9 port number that we just simply specifies that TCP needs to be used over here, and it just simply tells the potential for that. Okay, unlike TCP, UDP does not have a concept of connection establishment. It simply sends packets to the specified adjacent port. When UDP candidates are generated, they typically reflect actual listening ports where service can receive data. There is no need for placeholders like port 9 because UDP can directly send packets without needing to establish a connection. That's right. So in case of UDP, you do not really have port 9, but in case of TCP, you are gonna be having that. It's too much, yeah. There are a lot of things. Okay, let's talk about this offer. So layman's, ultimately, what is the offer? You create the offer that contains the kind of data that you will be sending to the other client, and that's it. So what offer it really means in WebRTC? The offer describes the first message in negotiation between two peers who want to start a real-time connection. What the browser is actually offering. In technical terms, offer is a block of text called an SDP. That's right, session description protocol. You can think of it as a menu communication options written in standardized format. That SDP includes what kind of communication does your browser want to establish, audio, video, or data channels. That's right. Yeah. Then technical details like codecs, VP8, and all these things, media resolutions, bitrate preferences, and support transport options, media direction, whether each stream will be sent or received or both. Each stream in the sense audio and video, if I'm not wrong. And ICE candidates that tell other browsers how it can be reached across networks. Essentially, your browser's offer tells other side, here's what I can send, what I want to receive, and how I'd like to do it. Ultimately, offer contains the information about you, your medias, your ICE candidates, and everything else. Okay, continuing from here, it even contains some of the ICE candidates too. Because an offer is just a text data structured as SDP, you can easily see it in your JavaScript console. Of course, you have to just simply go through this, and you will be able to see that. You can create the offer. Once the offer is created, you can just simply see the SDP. The SDP looks like a long structured document with the sections M audio, M video. They are the media streams, and many A lines, M lines define media type like audio or the video. A lines tell you which codecs are supported. RTP map over here. Candidate lines added later represent ICE candidates, the browser's possible network addresses. So ultimately, the offer does contain the ICE candidates. The text is this text is exactly what gets sent usually over WebSocket or HTTP signaling to the remote peer. That's right. Why is it called an offer, and who makes it? Okay. So the term okay, come on. So the term comes from session initiation protocol (SIP), and the other communication standards that WebRTC builds upon. And in those systems, connection setup uses an offer-answer model. So one side creates an offer, the other side responds with an answer. Both sides supply what they agreed upon as their local remote descriptions. Someone has to go first. WebRTC's design require one peer to be the offerer and the other to be the answerer. This doesn't mean one is permanently the caller or the host. It's just every connection negotiation round needs one side to start the proposal. Ultimately, one person, if there are two peer, one peer needs to just simply create the offer and send the offer to the other side. Someone needs to do it. Anyone can do that. I mean, of course, it's up to you whom you are gonna allow it. But yeah, In more advanced patterns like perfect negotiation, either peer can take turns making offers when negotiation and when renegotiating an existing connections. For example, adding new track or switching to the screen share mid call. Okay, that's fine. The takeaway: a WebRTC offer is your browser's initial proposal for a communication deal, written as structured SDP data. It's called an offer because it kicks off a negotiation. Your browser is effectively saying, "Here's what I'm capable of doing. What you would like to connect? Would you like to connect this way?" The other peer reviews this offer, decides what to accept or modify, then replies with an answer. Only after that handshake do both sides start sending audio, video, or the data streams and all. So this is how it's gonna be going on. Pretty simple. Okay, thankfully this got done as well. So let's continue. WebRTC internals. Ooh, WebRTC internals in the sense once the WebRTC connection is actually established, and if you want to know more about the connection, so you can just simply use these URLs, and that's it. You will be knowing more about them. So by the way, let's simply go through it really quickly. So other browsers offer features similar to Chrome, WebRTC internals for WebRTC insights. In fact, any browser that uses Chromium will have the same internal mechanism. Oh, come on, yaar. I should have mentioned Chromium earlier. I mentioned V8 engine. All the browsers they use V8 engines. Okay. Anyway, if they support JavaScript anyway, so that's possible. Okay, so uses Chromium. So I mainly wanted to talk about this. Never mind. So in fact, any browser that uses Chromium will have the same internal mechanism to monitor WebRTC sessions. What do I mean? Remember, Chromium-based browsers are like cars built using that same kit. So there is something called Chromium in browsers. If they are built using Chromium, they will have the same way to get the WebRTC internals. They all start with the same basic parts Chromium, but each company can add their own paint, fancy interiors. This is just the example. And special feature Google Chrome, Microsoft Edge, and Opera are all cars built from the Chromium carpet. That's fine. What this means is that all these browsers have similar functionality. Edge, WebRTC, internals, Opera, Chrome. That's right. When it comes to Firefox, so Firefox is a little different. Firefox is not built on Chromium. Instead, it uses its own rendering engine called Jacko. How to pronounce this? Jiko. Forget. This is why it has its own WebRTC stats interface, and is found in their browser by typing about WebRTC and also. This is how it's gonna be going on. So call it, consider it done. Session descriptions. We've already talked about this. What is a session description? Think of a session description as a detailed plan or agreement between two devices like computers or smartphones that want to communicate. This plan includes information how they will share audio and video. Description, right? Yeah, such as which formats they can use, codecs, and how they will connect. There are two types: remote and local and remote session descriptions. Local session description: this is the plan created by your device. It tells the other device what you can receive and what formats you support. You create the description. Yeah, that's right. For example, if your device can handle both MP3 and web audio formats, your local session description will include this information. That's right. Remote session description: this is the plan. This is the plan from the other device. It tells your device what a device can set, that device can send and what format it supports. If other device only sends MP3 audio, your device needs to know that it can adjust so that it can just simply adjust accordingly. For WebRTC connection to be successfully established, both local description and remote description properties must be set appropriately. Without setting both properties, the peers would lack the necessary information to establish connection, making it impossible for them to communicate effectively. Okay, consider it done as well. I mean, yeah, I'm able to understand, and that's what that matters the most. And we already have not a lot of things, at least now. So let's talk about connection right now. So during ICE candidate negotiation, your code has two primary responsibilities. Just a sec, give me a moment. Alrighty, coming back. Let's continue. So here we are. So connection, what is the connection ultimately? So during ICE negotiation, okay fine. Your code has two primary responsibilities: signaling server and client side. So signaling server accept ICE candidates received from one peer and transmit them to the other peer via signaling connection when on ICE candidate handler is triggered. On ICE candidate, yeah, that's right, makes sense. And the client side receives the ICE candidate. I will explain it. Never mind. Receives ICE candidate messages from signaling server, specifically when new ICE candidate message arrives, and then pass these candidates to your browser's ICE candidate agent by calling add this. That's right. Your code does not need to worry itself with the details within HTTP session protocol. I always try to adhere to KISS principle. Keep it simple, stupid. What does it mean? Your code doesn't need to worry itself with the details within the HTTP. Actually, you do not need to worry about the details that are inside the HTTP. You have to just simply make sure that it is attached, all the candidates. Once you send the HTTP, ultimately the offer, it is just simply added in the remote description if you are sending that anyway. So ultimately, connection means connection server. So there should be a WebRTC connection, or not WebRTC, WebSocket connection. So what will happen that once the candidate is generated, you will send the candidate to the socket connection or the WebSocket connection. WebSocket connection will send it to the other clients, and they will get it, and they'll be making the connections. This is how it's gonna be going on. Eastern servers. Here we are, everybody. Ultimately, what is the job of Eastern? There's a lot actually. Let's not worry about these things. Let's talk about Eastern server really briefly. What is the Eastern server? Eastern server, because look, by default, whenever you make a request, whenever you get the WebRTC connection established, at the time you don't know your public IP. You only know about your private IP, right? Because private IP has been assigned by your router. So now if you want to know and know about your public IP, ultimately if you want to know about your public IP and public port number, so what you will do, you will actually send a request to the Eastern server. As the Eastern server receives the request, it knows where this request came from. Hence the Eastern server will know what is your public IP and port. It will just simply send that back to you, and then you will be able to create Eastern servers using them. Create candidates using them. Anyway, let's continue. We are talking about Eastern servers over here. A simple server that tells you who you are, as simple as that. Eastern servers have one task: check IP and port address of an incoming request from a device running behind the net, that is right, and send that address back as a response. That's right. Anyway, Eastern servers don't have to do much. So relatively low spec Eastern servers can handle a large number of requests. That's why they are free. So congratulations, this is how this simply goes. So when it comes to this, so what will actually happen, that you will just simply send a request to the Eastern server. So sends a binding request to the Eastern server will get the request and will just simply send you the response that will contain your IP addresses and all. By the way, response with a binding response, XOR mapped address, private IP address, assigns new port. You want to know about your public IP address and port, Eastern servers are going to be telling you about that. So the term binding refers to the association between the client's private IP address and the public IP address port assigned by NET. The Eastern's response effectively binds the client's private address to its public address as recognized by external entities. What actually happens that by default, as a client, you only know about your private IP address, and now if you want to know about the public IP address, and they should be assigned as well, like they should be, like private IP address should be bound to bound to the public IP address. So once you send the request to the Eastern server will know all these things and will just simply send you the response back. Once the client received a public address, so once a client received a public address for itself from Eastern servers, it can then send these details to the other peer via signaling, that is right. The other clients need to know about your public IP address in order to initiate a connection with you, that is absolutely right. When client 2 receives your ICE candidates, it can attempt to connect it to your device using those IP addresses and port number, that's absolutely right. Each connection between two devices is identified by unique combination known as 5-tuple. We talked about this particular thing initially when we actually started working on this. The question: how does the router know to connect with your private IP? When a connection attempt is made to your router's public IP at this particular port, your router uses NAT to determine which device on your local network should receive the traffic. Ultimately, what happens whenever you send a request to the Eastern server, so at that time a mapping happens. So whenever the connection gets established, whenever you send the request via router, so router just simply creates a mapping using NAT, and that just simply maps your private IP and public port number, and whenever you get the response back, that is just simply forwarded using the same mapping. Alrighty, by the way, this much we've done. Again, this is just the public port. Okay, here you get many things. You get the address, candidate, component, port number, and ID. This is the ID, by the way. And apart from this particular thing, you have related and you have related port. Related means the private one, if I'm not wrong, and this is the public one. So this is the public IP, and this is the public port. This is the related private IP. This is the private port. Having said that, if I'm not wrong, okay. Alrighty, I should be able to see it here. Yeah, this one related. Yeah, private. That is the private one. Again, this is the public port. This is the public port for this number mapped by your router. So ultimately, public port is mapped via router, mapped by router via NAT. That can be used to establish a WebRTC connection. The router itself does not on this port. Instead, it performs NAT. So ultimately, it just simply says that okay, it is done by the router. Router does not do it directly. Rather, it actually uses NAT for that. So it performs NAT mapping to forward the traffic from its public IP and port to the corresponding private IP and private port to your local device. This is treated dynamically by WebRTC ICE process using techniques like Eastern and hole punching. Well, whatever this is. So ultimately, whenever you create a WebRTC connection, there's this mapping table actually automatically gets created. Ultimately, whether this is a table or not, that doesn't really matter. Your private IP and port numbers, they are associated with or they are mapped with public IP and port numbers respectively. And when it comes to your candidate, so it has this information. So it has so any candidate that you got, that will have these informations. Not just the candidate, it is actually a candidate object. So any candidate object will have these informations. So a candidate object will have the candidate ICE candidate prefix. Then it has this. That is the foundation group similar to candidate's priority. It has one components ID, usually one RTP, and 2 for RTCP. Then UDP, transport layer protocol. This is the priority value, and this is all about the candidate. This is the public IP, then the port number, then the type, that is SRFLX. That simply means it used the server reflexive. Ultimately, it used Eastern servers. And then we have related address, related port. That simply means they are the private ones. We have generations, legacy field, Chrome specific, usually always 0 if you find. We have username fragments used during connectivity checks. We have Chrome network identifier. It is mainly for identifying the network and all. And then lastly, we have identicates network cost, lower, better, and 10 off in cellular. Okay, that's fine. Okay, failure of Eastern server. Even though client 2 receives your ICE candidates, sometimes NAT might still block connections. Double NAT, complex NAT types, blocked protocols, etc. because of firewalls and all. And hence we are gonna be using we will actually be using TCP or instead of using UDP in that case. So I send the request, and the request is sent to the router. Router has its own I have my private IP address. Router has the public IP address, and then performs NAT translates to public IP. So private ID is converted to the public IP, and then this is sent to the another router, and this IP is seen as a private IP. This should actually be public one. Okay, never mind. So it is sent to the router 2, performs NAT translations, and then it is converted as public IP, and then ISP gateway. It may be blocked. So whenever you send a request to the other client, that may be blocked, and hence you need to take care of that thing as well. We have 192 private forms ISP gateway. Let's read about it. There's nothing in the diagrams now. More important thing is gonna be here. The protocol used by Eastern servers is defined by RFC 5389. It uses a simple request response mechanism where clients send a binding request to the server. Clients send binding request to the server. Yeah, that's right. Which then replies with their public IP addresses and port information. This Process can also include additional attributes like the type of net being used. So ultimately, when you send the request to the instance server, so what exactly happens? That's what being discussed here. There are several publicly available instance servers that developers can use during testing development without needing to set up their own infrastructure. For example, Google's public instance server at ultimately this is one of the instance servers provided by Google. Google actually provides around five public instance servers, and there are many other providers that do the same thing. Is widely used and all. That's fun fact. When establishing a WebRTC connection, both peers generate ICE candidates, which include potential connection endpoints derived from various sources like local IP addresses and via instance or relayed addresses via turn. The process of gathering these candidates is called ICE, and it involves trying out different combinations until a successful combination is established. Okay, that's right. Makes sense. There are gonna be many candidates, and only the best one is gonna be used for making a connection. So hence there's gonna be many, combinations. Alrighty, this thing we've gone through. Collapse this. Let's talk about turn servers. Turn servers are mainly gonna be used when turn server fails. So turn servers, when all else fails. So if turn fails, the browser will initiate a combination of turn servers credentials you supplied in the configuration field of the RTC BPR connection. When the browser sends a request to the turn server, it follows the turn protocol RFC 5766. Again, you do not need to keep all these things in mind. Ultimately, whenever turn server fails, then turn server is gonna be used. That doesn't mean that now turn server will be used all the time. After some time, when the turn server is back, turn server will keep getting used. Alright, anyway, this protocol involves specific message types such as allocate request, which tells turn server to allocate relayed transport address for the client. Okay, fine. Relay functionality. Turn servers. Actually, I've never used a turn server. So far, I've been working with the turn servers only. So we'll try it as well. Let's see in the future. So relay functionality. Turn servers act as intermediaries, relaying traffic between peers that are unable to establish a direct connection using turn servers. That's right. When a device behind NAT sends a packet to the external addresses, the NAT modifies the source IP and port. If multiple NATs are involved, NAT mapping can vary based on destination, and a direct connection may not be able to be made. What does it mean? When a device behind NAT sends a packet to an external address, the NAT modifies the source IP and port. If multiple NATs are involved, NAT mapping can vary based on the destination. A direct connection may not be able to be made. Okay, that's fine. Ultimately, there could be some cases where a direct connection is not possible to be made. In that particular case, turn is gonna come in role. By using turn servers, both clients can communicate through a consistent public IP address assigned by turn servers. This eliminates confusion caused by varying IP addresses. All traffic is routed through a single excuse me, turns out I'm suffering now. Okay, so ultimately what happens that whenever you try to make a connection to the other peer directly, so at that time they have their own IP addresses and all, and in between those IP addresses may change, and because of that thing the connection may not be possible to be established, and in that particular case turn server is gonna be used because it will have a fixed IP address. So you can make a connection to the turn server, another client can do the same thing, and then turn server will help you connect to each other. When all else fails, at the time this is gonna be used. That's right. So ultimately send the request to the turn server, other client will do the same thing. So allocating request using turn protocol over UDP, and then you are gonna be getting a response from there. Okay, fine. Wait a minute. When client 1 via ICE eject request a relay address from turn servers, it receives an allocated relay IP and port. In our example, this ultimately it got this right. That's right. But how does the client know to use this particular address? Please don't forget that even when turn servers are involved, you still need a signaling server to send a turn connection information. That's right, in the form of HTTP to the other peer. So the client, so the signaling server, which is separate from the turn server, must send the information to the client 2. Once client 2 receives the relay addresses from client 1 via signaling server, it can then use the same information, send media to client 1 through the turn server. So ultimately what is happening that instead of using using a turn server, because that of course failed, you are going to be creating a turn server. You will send a request to the turn server will give you the IP address and the port number, that is gonna be the fixed one, and you will be sending it to the other peer. That peer will just simply make a request to the return server, and now you both are connected to each other, but via a server that is called turn server over here. Bottom line, while the turn server provides the relay functionality, it is still a role of signaling server to communicate necessary connections details such as allocated relay addresses between peers and all. Okay, that's fine. When a client sends an allocator request to turn server, the net router treats this as outbound traffic and creates a mapping route responses back to the client. That's right. This mapping is stateful, meaning net keeps the track of the connections. That's right. These mappings these mappings allow responses from turn server to traverse back through layers of net because they match and establish the connection initiated by the client. Bottom line, if turn is used, turn is not used, and vice versa. And turn servers, vice versa, and turn servers have a conceptually simple task to relay a stream. However, unlike turn servers, they inherently consume a lot of bandwidth. Videos can be quite heavy, so we have to pay for turn servers. That's right. It is at the end of the day a fallback mechanism when both peers cannot connect directly despite attempting all available methods. It is built into WebRTC ICE agent framework, and it's highly optimized to send and receive data over UDP, user data protocol. Alrighty, turns out we have gone through the theory of this thing as well. Whew, last few things are remaining, bro. Signaling, and then there are ports and all. Okay, that's fine. Signaling. RDCP, it's gonna be much. No, it's not. Okay, RDC peer connection is the API key used by WebRTC apps to create. Hang on. RDC peer connection is the API used by the WebRTC apps to create a connection between peers and communicate data. Main task: gather the type of the data that the host can send and receive, codecs resolutions out of order, etc. This is the metadata. Gather potential network addresses, host, ICE candidates. Ultimately, once two tasks are done, the information must be extended to the other side through a signaling mechanism. That is also right. Signaling mechanism is the process of exchanging information between two devices. Offer metadata about the media to be used, routing, ICE candidates. That's right, and you have to send both the things to the other client using, of course, WebSocket. So there's gonna be signaling server. That signaling server will be using ultimately what it says that you will create the offer, you will send the offer, it will just simply forward the offer to the other peer will create the answer, it will just simply send the answer to the server will send the answer back to you, and then once it is done, then you will get the you will send the candidates to this. Candidates are gonna be sent to this one. It will generate the candidate, it will send back the candidates, and you will get the candidates. So once offers are exchanged, the answers are exchanged, the candidates are exchanged, then the connection is gonna be established. I know, quite heavy, but okay, never mind. How the information is sent to the other peer: JSON object over WebSockets. Yeah, you are going to be sending JSON objects. So SIP, come on, cancel. So session initiation protocol, SIP, is an actual protocol that works over IP. You can use with the Node.js using JS SIP library to perform signaling for WebRTC. New words, invite, acknowledge. I mean, this is just the another way. I mean, this is also one of the ways. The another thing is that you can use WebSocket for that. Okay, so the first way is that you can use JSON objects over WebSocket. So using WebSocket, you can just simply send the request to the other peer. This is the another way. Just know about that. That is the simple. That's the simple thing. So session initiation protocol SIP is an actual protocol that works over IP address. You can use it with the Node.js, for example, using a JS SIP library to perform signaling for the WebRTC. Wow, you can actually send the data. New words that you need to know: invite, acknowledge, byte, register, etc. Ajax, you can just simply use Ajax for that. We have XMPP. These are just the methods to just simply send the data to the other peer. Again, we are gonna be using the first one. Anyway, XMPP is extensible messaging and presence protocol is also protocol. Various libraries that you can use. Just a sec. Extensible messaging and presence protocol is also protocol. Various libraries that you can use. XMMP with jingle. Okay, these are the ones. Keywords are gonna be these. These are just the keywords. Bottom line, signaling methods are not specified by WebRTC standards. You have to build your own server or libraries for signaling. Ultimately, you decide what tool you will be using for sending the message to the. sending the offer answers and candidates to the other peer or exchanging them, and that's it. It's completely up to you. When it comes to code, so this is the code. Congratulations. Let's simply go through the code exactly, see what am I doing here. So actually in the first go I actually used the cache then way of getting the response, then I started using async and await. So that's fine. It's sort of the same. You have the instance servers over here. I mean, things are exactly the same, so I'm not going to be talking about the code over here. It's pretty simple. We have already talked about this in the beginning. The only difference is that right now I'm using async await. Earlier I was using catch then in catch block. I think I need to go through it. I mean, there are some special things at the end. First of all, you have normally your HTTP code, HTML code. You have the video tag, and you have just another video container that will be added here. You have the PC null by default, and over here we try to use then catch block, and then we switch it to this async await. That's fine. So got the local stream. Once I got the local stream, added to the video element. And after that we created our own peer connection, but before even that we had to have our WebRTC configuration. Inside that I have iServers. There can be many iServers over here. Once we have the iServers, this is the first way, this is the another way, so you don't really need to worry about them. You can just dig deeper into them. Then we created the peer connection over here. Once the peer connection is created, on negotiation needed, handle this. We have the tracks, so we are getting the tracks from the local stream. After that we are just simply adding them to the peer connection. Then on negotiation method will be triggered, hence offer is gonna be created. Of course you can even modify the HTTP set as receive only. The thing is that by default ignore the background noise. By default HTTP supports both receive and send. You can even modify it. Modifying it in the sense you can type is always gonna be the offer, and SDP is gonna be modified SDP, and inside the modify SDP what you are doing, there must be a function for this anyway, so you can just dig deeper into it. We are modifying it. For modifying it I'm using this modify SDP. Modify for receive only. That simply means somewhere here at the bottom I have a function. Let me see if I have. This is the one, modify SDP. So I get my SDP, and from the SDP by default I have send and receive both. I'm gonna be replacing it with the receive only. So hence once this particular line is replaced, it will only be it will only be the receive only. You cannot send, you can just simply receive. So this is how it's gonna be going on. So okay, this thing we have gone through, and then the next one is get stats. You will be able to getting the stats of your connections. So stats for each report, that's fine. On as candidate, this will be triggered whenever the candidates are created, and this particular thing is done as well. And then you have handle negotiation needed. Over here the offer is gonna be created, and then here you are getting the information of the devices, and that's pretty simple. Yeah, sort of we've done with this. Yeah, that's right. Okay, so we've gone through this. This is nothing but the style, and also let's not worry about that. This was all about the code that I have written. This is the most basic code anyway, because even we have built a proper video calling applications. I still have to deploy that. I will be deploying it using Kubernetes. Over there we did work with the peer-to-peer connection, but there were multiple peers. PC direct this is just the normal info. Let's simply go through it. Connection exchange directly found on the PC object in public property called on connection state change. Okay, triggered whenever there is a change in the connection instead of this. These are just the events. Okay, you can just simply read more about them. We have signaling state change, we have stable, we have local offer. This is the local description, description state. This could be stable, have local offer, have remote offer, have local offer, pre-answer, okay, have no idea about this, but probably this is something. Okay, let's not worry about that. These are the types of the states first of all, and apart from this particular thing, there are gonna be specific states regarding these specific events. You can just simply dig deeper into them. You can know more about them, and all these things are gonna be automatically rendered on the WebRTC internal. So whenever you go to that particular page, all these things are gonna be shown over there. Lastly, we have the data channels over here. Data channels are mainly gonna be used for specifying what kind of data you wanna send, and you can send the data using the data channel. Every data channel is associated with an RTCP peer connection. The word channel means a dedicated pathway for transmitting data between two peers without server, and WebRTC uses various protocols to transfer data over the wire. For example, when we use data channels, WebRTC uses DTLS, SCTP or UDP. Remember, every piece of data sent over wire travels through different components of a network. Each component handles a different part of the communication process. If you are curious, know more about you can just simply learn more about that. Ultimately, RTCP peer connection, PC.create data channel. You can actually create a data channel. Once the data channel is created, being an object, you have various properties and methods. There are two methods: send and close. Since it is just like WebSocket only, but here you have two methods. You can close the data channel, you can send the data using the data channel. So first of all, you have to create the data channel. Once that is created, now you can just simply send or close. Since the data across the data channel to the remote peer, and the data can be found in string and all this format. Every peer connection object can have up to theoretically maximum these many things, channels. These many channels actually can be there. That's insane. SCTP uses a 16-bit field to identify strings, which allows it to manage. I will explain it anyway. To manage multiple data channels simultaneously, the maximum number of streams. I don't know. Okay, that's fine. The only offerer, the peer, can initiate the connection since call peer data channel method on their RTCP peer connection. The offeree, the person receives the WebRTC request, will listen for the on data event on their on RTCP peer connection object. A data channel event is sent to the RTCP peer instance when the RTCP has been added. A result of the remote peer calling. Okay, fine. Let's keep it simple. What is going to happen, that there are going to be two peers. You will be first of all getting a WebRTC connection established between both of them. Once a WebRTC connection is established, then a data channel will be created, and the data channel will have few methods. So once the data channel is created, the data channel has send and close. So using send, you can just simply send the data from one peer side. It will be listened on the other peer side. So for sending and for listening, you have different events, and this is how it's going to be done. For sending, you have method. For listening, you have events. I do not really have the code over here. Yeah, that is right. But overall, we have gone through everything. Congratulations, it is done. I mean, there's really nothing else right now. I know it can be a little confusing. RTCP is just RTC SCTP transport is just an object that describes the transport details for your data channel. That's right. You can't create this RTC SCTP transport object. Instead, you are given access to it via SCTP property on the peer connection object. That's why I took time. Okay, let's forget about this. Okay, overall things are done. Now the last thing that we can actually discuss, or actually see the example of this thing, because I've forgotten. Ultimately, what happens, you do create a data channel, but once the data channel is actually created, I already have a code written. So once the data channel is created, RTC SCTP is actually used over there. So let me go through the code really quickly. So WebRTC, not this, video calling, probably this only. Just a second. Probably this one. Let's see exactly what am I using here. So what am I looking for? I'm looking for where this data channel related stuff is actually happening. So inside the server, send on hand rage, disconnect. Socket.io is being used over here. That's interesting. File transfer. Okay, we are sending the files using socket.io, not here. Somewhere else I definitely did this, I forgotten, but never mind. Mic, camera, screen share, load audio, connection status, update media sender. video process. Definitely data channel is not being used over here because we are using socket.io if I'm not wrong, but I'll have to still see. On ice candidate, on track, set offer, that's fine. SDB process, close connection. It turns out to be like that. Okay, let me see properly. People and okay, document, click chat heading. I definitely wrote the code, but I'm not sure where. Custom file label, this. It is using socket over here. So file transfer to others. So ultimately for transferring the file, it is not using data channel, rather it is just simply using the socket.io for sending the file to the other peer. So this is not the project that I'm looking for. Google Meet app, it's definitely not gonna be here. Let me see, explore this one. Otherwise you can just simply have a look at one of the examples online as well. But I'm sure that I wrote it somewhere or the other. Ajax state util WebRTC handler. We did it here in this one. How can I be sure about this? Again, I'll have to go through the whole code ultimately over here. WebRTC configuration is done. I know here it was done, I remember that. But when it comes to this one, so I must be creating the WebRTC. ICE candidates generated, ICE candidates received data channel. This is where the data channel is going to be used. The question is how many times I'm using it here. At 25 times. Alrighty. So here create data channel. So data channel was actually created. So create data channel is actually a function. So first of all, you are gonna be listening for the message on this particular event. So on data channel. So whenever you get a data from the other peer, you are gonna be receiving the data over here. Once you receive the data, e.channel will actually have the information of your data, and that is once you have this data channel. Let's have a look at this properly. First of all, we have this. Then you start WebRTC process. We have the offer over here. Okay, that's fine. And DOM offer, this is fine. Utilities, update UI button, that is also okay. So create a connection. This is where we are creating the connection. We have RTC PPR connection, and we have local stream over here. So this is the local stream. And once you have the peer connection, so we have on track event. We have just on track event, PC add event listener event. Add event listener for what? PC add event listener connection state change. So whenever the state changes, at that time it just simply triggers, and it will just simply show some messages over here. That makes sense. There can be many events. So this is one of them, signaling state change. This is another one. Then ICE candidate, whenever you receive the ICE candidate, so this is done. Data channel is not here yet, so create data channel. Am I actually not creating the data channel here? I think I should be creating inside this. Alright, just a sec. Once we received the ICE candidates, the data channel hasn't been created yet. UI utilities. So where am I actually using this particular function? Create data channel. I cannot believe that I'm not using it here, literally. Probably this is not needed. Create a peer connection object. So whenever the object is created, data channel, that's not created. Okay, when we click on send button, at that time it should be created, right? So that makes sense. So this particular thing is done. Anyway, we are not doing it here. We are just simply listening for some of the events, and that is it. Create data channel. So this is the function that simply takes just checks whether you are the offerer or not, and on the basis of that thing, it will just simply get this particular object, and it will just simply create the data channel. Once that is created, Then using the data channel, you will be sending the what? You will be sending data. So register data channel event listeners. Over here we have some of the event listeners, so you can get message over here on the data channel. You can close the data channel, you can open the data channel. Once the data channel opens, so this is what gets logged. When it closes, this is what gets logged, and when you get the message, you just simply get the message. I'm sneezing a lot today. Alrighty, so this is what happens. So ultimately, once the peer connection is established, you have to just simply create a peer connection. Then on that particular peer connection, you can call a method that will be creating your data channel. Once the data channel has actually been created, so on that particular data channel, you can add some of the events. One of the event is message, another one is close, another one is open. So whenever you receive the message, that message is gonna be received using this particular event over here, and you can just simply then use that particular message whichever you want. And the another thing is that as far as excuse me, as far as sending is concerned, you are gonna be sending using this data channel only. So let me see where am I using that. Handle offer, handle answer, not this. Send message using data channel, this is the one. So you got the data channel. It is simple. So simple. Listen for the events using the data. First of all, create the data channel. Then second, listen for the events using the data channel, and then using the data channel dot send, you can just simply send the message. So whatever message you want to send, you can call this particular method. The message will be sent. If you want to listen, so for listening, you already have a data channel dot add event listener. You have message, you have close, you have open, all these things, and this is how things are gonna be done. Alrighty. By the way, we've done that. Okay. Anyway, let's simply close everything. So ultimately, WebRTC was the sort of a pending topic that got done here today, and now I don't need to worry about the WebRTC ever again. Okay, the prepare environment. What is this prepare environment? Node.js. This is just the starting files, and also let's not worry about them. So okay, this was the first thing. Second was, there are two more things. First of all, I needed to talk about gist, and the another thing is that I needed to talk about I had a project actually, web project. That is sort of the edtech one. I have to go through that. How long has it been? It's already been 1 hour and 42 minutes. That's great. So the next thing that we are gonna be focusing on, that's gonna be this project. Again, I will take a break and then I'll be back and continue on that. That's actually gonna be this project. So there's front end, back end both. The code is written, but it hasn't been checked, and there are many errors that is for sure. So we have to just simply resolve the errors, and this is how we are gonna be going ahead. So let's see, we have to mainly focus on the front end part. Back end is almost written, but we have to connect our front end to the back end. Even the code is written, but we have to check whether there are errors. If there are errors, we'll be fixing the bugs, and this is how we'll just simply get it done. So almost we have to make it working ultimately, and once this is done, then the job will be done. So I'm gonna be back after some time, and then we will start working on this thing. Until then, take care. We completed one section, that was WebRTC one. At least one headache is less. That's gonna be not a lot of headache. Okay, by the way, I'm gonna be catching up soon. Until then, take care. Bye bye.